Now we're at the final question of the CSSA 2010 Extension 2 paper. So this is question 8b. This is one of the few questions that require a little bit of insight, and it does get quite exciting near the end. Now, the first step was they wanted you to show that for k is greater than or equals to 0, that 2k plus 3 is greater than or equals to 2 root k plus 1 k plus 2. Now, the way you go about these questions, especially when you're asked to prove something and you don't know where to start and how to write the algebraic gimmick that's attached to it, is you take your booklet, you slide it over to the left, and on this side of the page, you do a bit of rough work here. So you ask yourself, what would happen if I was to square both sides? If I square both sides, I'm going to get 4x squared, and I'm also going to get the 12k, and plus 9. And on the right hand side, now just put a little circle here because you're not claiming that it's greater than or equals to. You're just contemplating what's happening if you were to do the same thing to both sides, like an equation. Right? You just don't know if it's greater than or equals to or not. Okay, and then you go, oh right, let's square that. So it's 4 outside of k squared plus 3k plus 2, which is the same as saying 4k squared plus 12k plus 9, 4k squared plus 12k plus 8. Well, come on, 9 is greater than 8. So, is your proof done? No. That's the reason why you write it over here as rough work, because in the actual proof, you get real sneaky and you go, well, magically, we know this. Okay? So this is where the proof actually starts. We know just from the middle of nowhere, no, actually we know it from here, that this is an obvious fact. Okay? We didn't actually just go, oh, I magically knew that I needed this because this is what this is. We don't know. I mean, you don't know the relationship between them. You can't just see that and go, oh yeah, we're going to start our proof there. How do we know to start our proof there? Because of the work we did here, of the sort of tinkering around we did here, that's how we know. So in the actual proof, you go, okay, great, fantastic. Don't cancel anything out. You know the left side is a perfect square, so that's 2k plus 3 all squared is greater than or equals to. On the right side, you factorize the 4 out, and you realize that it's just this. Fantastic, and you square root both sides because they're all positive anyway, since k is positive, and there's no issues with this sign, so 2 outside of what you want. Not a difficult 2 marks at all if you know where to start, how to start it. If you decided to start from this line at the beginning, what you want to prove, and all you wrote was this is greater than or equals to that, greater than or equals to that, because you just squared everything and tried it, that's only going to give you 1 out of 2. Okay? It's not going to fly. It's not going to give you full marks. So it's good for working out how your proof is going to look like when you finally finish it, but this will not award full marks. Now in part 2, this is where it gets exciting. It says to show that when n is greater than or equals to 1, 1 plus 1 on root 2 plus 1 on root 3 plus, so all these roots, plus 1 on root n, so up to root n, is apparently greater than 2 outside of n plus 1 minus 1. Now, in this sort of situation, you've got to think, how can I use the earlier parts of this question on this one? I mean, how can we use this to help us with that? Because, firstly, the square roots are not on the denominators here. And secondly, there is no product of 2 numbers in these square roots. And thirdly, if you increase k by 1, this is going to go from 2 to 6 to 3 times 4 is 12. But these are going up 1 at a time. So we can't directly apply this to that just yet. So we've got to explore alternatives, and this is where the high band 6s are made, is when people realize, when you look at n greater than or equals to 1, you realize, hey, this is a proof about integers, starting from the integer 1, going up, and you're trying to prove this is true for all integers. Just the way I said that. If you thought about just then about the idea of induction, then you're on the right track. If you were to do this induction, obviously you would test n equals to 1. So 1 is just the single term. Is it greater than 2 outside of root 2 minus 1? Well, I believe so. It works. Now, the next step is you go assume that 1 plus blah, blah, blah up to 1 on root k is greater than 2. It's your inductive sort of assumption, minus 1. Okay, and now you say let n equals to k plus 1. So when you let n equals to k plus 1, you're asking yourself, is this true? Can I prove that 1 plus everything up to 1 on root k plus the next one, 1 on root k plus 1, is this somehow greater than 2 outside of root? Now this has become k plus 1 now, n is k plus 1, so k plus 2 minus 1. Is this going to really work? Well, fortunately, what we do know is that the left-hand side, okay, this is where we use the assumption now. We know that the left-hand side is equals to 1 plus everything up to 1 on root k plus 1 on root k plus 1. Now, this portion of the left-hand side is, according to our assumption, greater than 2 outside of root k plus 1 minus 1. Okay, so your goal now is, can you prove this is still greater than that right-hand side? Can you, from this point, prove that it's greater than the right-hand side? Well, fortunately, we can. But in order to know the pathway, how you fully write it out, it's that over the page trick again. So let's have a look at what we want to prove here. We want to prove that 2 outside of k plus 1 minus 1 plus 1 on k plus 1, this is somehow greater than 2 outside of k plus 2. Okay? Now, in certain situations, you're not allowed to actually well, in this case, let's expand it. So 2 cancels out with a 2 here, and we expand this out to give 2 outside of, k plus 1 square root all squared plus 1. I've multiplied the left and right by k plus 1. Okay, k plus 1, k plus 2. This looks very promising because this looks just like the what we did before. In fact, this is the statement from part 1 of the question. So what you do here is now you know the interaction between part 1 of the question and what we're trying to prove here. So you say, but since from part 1 of the question that 2k plus 3, k plus 1, k plus 2, we're going to really just tweak things around and try to work backwards here. We're going to go, all right, okay, let's just rewrite that as a 2 k plus 1 in brackets plus another one greater than or equals to 2 outside of root k plus 1, k plus 2. And now we're going to divide both sides by k plus 1, so that becomes 2 plus 1 on, sorry, that's not a 2, that's 2 root k plus 1. So we're dividing both sides by root k plus 1. Great, and now all we have to do now is just minus 2 from both sides. So we have 2 bracket that should be a 1 there, sorry. Now, this entire part here has been a deduction from part 1 of the question. Nowhere have we used anything we're trying to prove. All we're doing is deducing something from information we know much earlier in part 1, something we've already proven. Right? Something we've already proven is from part 1. But this line, this final line, okay, combined with this bit of working out, creates another descending order. It creates the fact that the left-hand side, according to our assumption, is greater than this, which is the same as this, which is greater than that. So left-hand side, which means 1 plus everything up to 1 on root k plus 1 on root k plus 1 is. I mean, if think about it, a is greater than b, which is greater than or equals to c, then clearly a is greater than c because it's in descending order. So, and c in this case is just 2k plus 2 minus 1, right? And that achieves our inductive step. So you can say, therefore it's true by induction. I mean, you can blabber on a little bit, but once you achieve this step convincingly, it's true. I would sort of elaborate on. Look, frankly, if you can get to this conclusion in a legitimate fashion, people who mark for you don't care. Just secretly saying. They'd be stoked if you can actually get this far. Now, for part 3, if you can discuss the validity of this statement, well, they want you to think about the idea that, hey, the sum from k equals to 1 to n of 1 on root k is less than 10 to the power of 10. Now, 10 to the power of 10 is a really big number, but we've also, is this even true? Well, according to part 2, we're told that 1 plus 1 on root 2 plus 1 on root 3 plus all the way up to 1 on root, we'll call it n in this case, capital letter n. This is greater than 2 outside of root n plus 1 minus 1. Now, this is a function that is a non-asymptotic function. And the significance of that is that no matter what number you pick, any large number, there is a value of n that will make this function greater than that number. Don't believe me? Well, let's look at, for example, let's pick this thing, minus 1, and make this equals to 10 to the power of 10. So, square root of n plus 1 minus 1 equals to 10 to the power of 10 divided by 2. And we're going to add 1 to both sides. So, root of n plus 1 is equals to 10 to the power of 10 divided by 2 plus 1. And n is really the square of this giant number minus 1. So, if all we did was if n was greater than 10 to the power of 10 on 2 plus 1, remember, this is not infinity or anything like that. It's just a finite number. It could be a big number, sure, but it's a finite number. So if n is anything greater than that, for example, just take away the minus 1, then the summation from k equals to 1 to n of 1 on root k, right, which is our left-hand side, the left-hand side, is greater than 10 to the power of 10, because that's what it says, right? If n is this number, n is this thing, you get 10 to the power of 10 exactly, right? Let's just write it properly. It's greater than 2 to the power of, it's greater than that, and because we know that this is an increasing function, and as n gets bigger, if n goes past this point, as we said here, this number will be too big. In fact, it will be bigger than 10 to the power of 10. So yeah, it's false. Now, whether the exam will award you full marks for saying the word convergent, divergent, I think that's more of a tertiary term. So I would really recommend, if you still have time at the end of the exam, to work out an explicit value of n to demonstrate that once n gets past this point, this sum from part 2 is greater than this. But we know that if we substitute n is this into that, well, something greater than that into that, this is going to end up with a number that's bigger than 10 to the power of 10. And we're finished.